Check.
Hey, all right. So this is a fairly technical topic. Just kind of want to know, have any of you guys looked at Windows kernel device drivers before? 1, 2-ish, maybe 3? That's actually about half, so it's not too bad. So my name is Steve Vittitoe. I am a researcher with Google, and I work for a team there called Project Zero. The goal of Project Zero is to find zero-day vulnerabilities, report them under a very strict deadline of 90 days, and apply pressure and leverage to vendors to fix their bugs, rather than report a bug and then wait 3 years for this information to never be fixed. So my contact information is here. @Bool101 is Twitter handle, bool@google.com if you want to email me. And I've been on this team about 8 or 9 months now. And before that, I've been doing reverse engineering. Before Google, I was at Endgame doing very similar sort of things, which is Endgame is a defense contractor. I spoke here last year with them in mind about playing Capture the Flags, which has really been where I picked up a lot of the skill set. So I would encourage you to play Capture the Flag, and if you haven't checked out the one here, it's supposed to be pretty good. Some pretty tricky problems. Real quick outline about what I'll tell you about AFD. So I'll tell you number one, why I'm talking about it. There's about 50 device drivers in Windows when your machine first turns on. So why pick this one out of all the others? And it's not because it starts with A at the top of the list either. I'll give you a quick WinSock overview. WinSock, if you're not familiar with it, is the architecture in Windows that lets you do socket communications. So if you want to open a socket to a mail server and you do, socket, connect, send, receive, that's all going through this WinSock API, and it has a user mode component and a kernel mode component. It kind of works together. That's different from the Linux version where everything is kernel mode. In kernel mode, you just make a syscall to open a socket and you get a file handle back. In Windows, there's actually protocol abstraction that happens in user mode. So we'll get into a little bit more about that. I've got a really great diagram that sort of draws it out very clearly. Since this is a reverse engineering talk, we're talking about how does this work and why. And I'll tell you some of the interesting things that I found along the way. It could be just simple observations, or it could be there's a bug there. You never know what you're going to find when you get into this kind of research. It is one of the things that I really like about doing it. I'll tell you a bit about the analysis that I did. So when I started this, it was to find zero-day bugs, and it was an effort in looking for exploitable conditions. And I'll tell you what I did, and I will also tell you at the beginning that I have no exploitable conditions out of this driver. Microsoft has really done a very good job with it. And in some sense, you're documenting a failure with that. But if you fail to find bugs, you've at least provided some level of assurance that the driver can withstand, n number of weeks of analysis from an attacker perspective. It gives you kind of a sense of the cost that would be involved to attack this vector. I did a bit of fuzzing on this driver as well. I'll tell you a little bit about how I set that up. And I had maybe 1 or 2 clever ideas, but it was pretty basic in the end. And research is something that never ends, right? You start it and you ask a question, which invariably leads to more questions, and hopefully you can answer some along the way. But the more questions you have, the more ideas you have for future work. So I put together a little bit of what I think the way forward with this should look like. Okay, so what is AFD? It's a file, right? So it's in C, Windows, System32, drivers. There's a file, AFD.sys. It's about 500K. You can look at the properties on it. It gets loaded by default every time you turn on any Windows computer, all the way back to Windows 95, right? This is an old driver. And it's still in Windows 8.1, right? The same concepts have been there for the last 20 years. The name on it is actually kind of funny. So it's called the ancillary function driver, which I have no idea why they would name it that, except I heard a rumor, and this is maybe a little bit of Microsoft lore that is unconfirmed, but when this was first being developed, anyone want to take a guess at what AFD? I told you last night. That doesn't count. So AFD was another fucking driver, and they had to change this before release. So I cannot attribute a reliable source to this, but I like the story, so I thought I'd bring it up. And AFD is the ring 0 portion of WinSock. So you have your user mode code. whenever you make a socket, this is the first stop into the kernel, right? This is where it goes. This is what handles that whole interface in the kernel. It's also used as a kernel service provider. So not only can user mode components talk to it, other kernel drivers can talk to it to make socket calls in the kernel. And that was something that was new that was introduced with the Windows Vista called WinSock kernel, aptly named. You should realize that this is not the only way you can make network communications in Windows. Well, just off the top of my head, there's like 4 other things that you could use. So there's WinHTTP that will talk to HTTP.sys. You can also start servers with that. There's WinINet that will, it takes a different path. It doesn't use AFD.sys. There's WebDAV, right, for like file shares over HTTP. And that's also a kernel interface that you can talk to. And there's MRX SMB, or like the SMB client, which is implemented in the kernel as well. So all of these things can do network communications, and it's not like this is the only one that can do it. So it's not because it starts with an A. It's not because it's been around a long time. It's not because it's the only thing that can do network communication. So why are we even talking about it? It's because of sandboxes. So sandboxes are a really, really great defensive technology. So you run a browser today. Let's say you run Chrome. You have like 3 Chrome processes that start up when you run your browser. A couple of those are really, really locked down. They can't touch disk. They can't touch network. They can't talk out using standard APIs. But this device that is created by this driver, so drivers create devices that you can talk to, like a file. So you could do create file on / device / AFD / anything you want. Give it a context or a namespace at the end. And it would let you open that file, and then you could interact with it as you would any other thing on your system. And this device that is created by AFD is accessible from every sandbox that we looked at. So Chrome sandbox, the Internet Explorer and Enhanced Protection Mode sandbox, Adobe Reader sandbox, and the default restrictions on it. So files have permissions that you can assign to them. Devices have permissions that you can assign to them. Everything in Windows is an object that has permissions associated with it. And usually, Microsoft does a very good job of carefully locking these down and carefully controlling who has access to this. In this case, AFD has read and write to everyone. So you can do this as a guest user. Talk to AFD, talk to the kernel on this other input. Likewise, when we realized this, we realized that there was also a history of bugs with this driver. You can search CVE and AFD, and you'll get 3 or 4 hits. One of them is kind of lame. I think the 2012 or 13 one was actually just an information disclosure. It wasn't a full code execution bug. It leaked a kernel pointer back to you, so you could tell where things had been randomized in ring 0, which defends some depth. That got patched. The one that was most interesting was the one last year that was it was a dangling pointer bug. So something got freed, a pointer was still around, people were able to use it and then exploit that bug. But that bug fetched $100,000 at the Pwn to Own event in CanSec. So that's another reason why it got kind of brought to our attention. So Project Zero, when it was created about a year and a half ago, had a mission statement that was very simple, which was people are getting attacked with zero-day vulnerabilities, and we can throw all the appliances we want at this, and we can throw all the user education we want at this, but if you're running vulnerable software and people can connect to you and exploit those bugs, there's no IDS signature for it. There's no user education to not click on a link. The only real way that's been effective in the past is to patch the bug. And to patch the bug is a hard problem because there are so many attack surfaces and there are so many potential bugs. So how do you go about solving this problem of making 0 days harder? And notice it's not make 0 days impossible, right? We don't think that's a realistic goal, but to make them more difficult to exploit, to raise the cost of exploiting a 0-day bug is sort of the mantra of the team. And we have 3 ways that we're going to go about doing that, but one of them is strengthening these sandboxes. So we've known for a long time that Adobe Flash is really a soft target. Anyone can take a fuzzer, find 1,000 crashes in it, and maybe 3 of them will be exploitable, and you can have a 0-day bug with a couple of weeks of research. And a 0-day bug in Flash would get you into so many places that it is a very, very cheap thing to do for the amount of payoff an attacker would get. So we put Flash in a sandbox, right? So Flash, even if it's exploited, can't persist. It can't write a file to your startup directory to load malware. It can't interface with other bits of the system. And thereby, an attacker needs not only one bug to exploit, say, Flash in the first place, but they need a second bug to get out of the sandbox if they want to interact with the rest of your system. And that's a pure cost metric. You need 2 exploits to conduct an attack now, not 1. So we start looking at ways to break out of sandboxes. The biggest one has probably been logic errors, where you have a sandbox process, but it actually does need to touch disk. So you create a privileged process that can talk to the sandbox called a broker, and then the sandbox process has some method of communication between itself and the broker. And that's software that can be attacked, right? So there's an IPC mechanism between these 2 processes, and there's been logic errors there, so that you could make it write to a different file path, or you can make it handle a token improperly. The other big one we see are bugs in the kernel. So your sandbox is only as strong as the kernel that it is running on. And the biggest one we see is Win32k.sys, which has something like 1,200 system calls you can make just for GUI processes. And it's incredibly object-oriented in the kernel, so you get a lot of really weird and interesting bugs. We're fuzzing that, by the way, so we will have raised the cost there as well as a patching the zero-day vulnerabilities. And then there's the accessible devices. So these aren't paid attention to as much as the other 2 attack surfaces. And the pwn-to-own bug, which I would say it's sponsored by Google as well, helped raise our awareness of this possible attack surface. So, and the interesting thing about this is that it wasn't even considered a security boundary, even with the history of bugs, even with accessible sandboxes. You can't even turn it off until Windows 8. And even then, it's not trivial to do that. You have to create like a lowbox token and an app container, and that breaks a whole lot of other things on your system as well if you're doing any kind of real processing. So not able to be disabled attack surfaces are even better. And when we take a real quick look at it, I mean, just looking at things like file size and number of methods it has to support system calls, you find that it is actually a fairly complex thing. And it is not something that's trivial to get through and reverse. And complexity being the enemy of security, is harder to verify that the driver is doing what it says it's supposed to do. There's also a couple of interesting choices that Microsoft made when they were developing this. Number one is they put all of the SAN communications, so like storage over a network, is implemented largely in AFD. So this is not only for sockets, but also for network storage and kernel clients coming in. So there's a few things happening here that's more than just what it looks like on the first blush. This is what WinSock looks like. It's a little dated. The WinSock current version is 2.2, and this shows 2.0 up here, but it presents the sort of the stack that you go through. So across the top, you have your applications, be they 16, 32, 64-bit, and they invoke WinSock, which loads a library into your process. It's ws232.dll that gets loaded, and that sets up some initial space for this socket communications. From there, you say, I want to open a socket, and you do that with the socket call. You tell it what kind of socket you want to open. So AF_INET is a socket for communicating with TCP/IP. AF_IRDA is a socket for communicating with infrared data. So there's a handful of these that are supported by helper DLLs in WinSock. So there's TCP, NetBIOS, IRDA, ATM, and there's a few other new ones that have been up there as well. The funny thing about this, though, is as soon as you call into WS232 sockets function, the first thing it does is call another function in WS232. It's just a simple wrapper calling this WSA version of the socket, which very quickly hands it off to this other thing called MSWSock. And you bounce around in there for a little while it's trying to figure out which helper DLL you should load based upon AF_INET. And that will load the appropriate helper DLL WSH TCP/IP for you. That will set up context that will maintain state of your sockets for your program, and it comes back out to MSWSock, which actually makes the ioctl. So it's not like you make a socket call to WS232 and then it talks to AFD. It's this whole user mode architecture, and this is designed to support things like the old layered service providers in WinSock, and that whole architecture that you can configure on a machine to take advantage of some of these hook points that it gives you. So down here you see AFD.sys talking to the TDI layer in kernel mode. This one's kind of funny, this msafd.dll. In reverse engineering, I never saw this come up as like anything ever used it. So I went and pulled it and looked at it, and it is literally an empty PE file. There's nothing in there. It has one DLL export that points to MSWSock. So it's got to be for old legacy compatibility reason, but it was kind of funny to see that you have empty PE files on Windows that do nothing but redirect legacy hardware to the right spot, or legacy software. So in this regard, AFD is really a proxy. So you can think about it as I'm taking these socket calls, I'm translating them in user mode for something protocol specific. You're talking to me in AFD, and then AFD, that's not your NIC driver. That's not sending out packets for you. That's talking to something else. Historically, it talked to TDI, which is a very, very well documented structure. And you can find out lots of information just in the DDK, the device driver development kit, or WDK now. We'll tell you all about how TDI works. In Vista, they added on WSK. So when you make these calls, you can go down one of two paths. You can be a proxy to TDI or a proxy to WSK, and the type of call you make depends upon which way you go. So yeah, it includes send requests, and again, the kernel mode clients can also talk to this. And the kernel mode clients then become a client to the WinSock kernel provider that is enacted by AFD.sys. So, okay, we have we've scoured MSDN, we've done basic analysis on this driver and its helper functions in user mode and kernel mode. Let's open it up and take a look at it. And the first thing that you notice is, oh man, there's all these great strings that tell me what function name is and what the length of this thing was that really aid a reverse engineering process. And you look at the cross-references to those strings, and they're all debug prints. And I don't know about you, but like when I write software, I strip all that debug print out. It adds space, it adds overhead. Those are actually getting called when you're running this driver in a real environment. And if you turn on your debug prints, there's a global flag you can do that with a kernel debugger. You'll see all these messages come through of these debug prints that are left in drivers. And got me thinking just a little bit, how many drivers actually implement debug print? How many of them are doing this? And it turns out it's about 25%. So of the 280 some drivers that were on a system, 74 of them imported debug print or debug print EX. I don't know why. This has to be like a debugging thing for Microsoft, but they've enforced to their device driver manufacturers to use this system called event tracing for Windows, or ETW. And you see lots of ETW code in AFD as well. So it's not just for event tracing. It's like they forgot to remove it. And that to me is a sign of poor control on release of code. Like, did anyone statically reverse this before it was released? And red flag number one, yes, we should look here because of all the other reasons and because of this. Really, that hypothesis did not turn out to be true in this case, as the analysis that was afforded this driver did not result in a bug, but it was incredibly helpful to the reverse engineering process. So if you wanted to tear apart a Windows driver, I would suggest that you look for some of these with debug prints, and that will make your life easier. On initialization, so you write a C program, you started at main. You write a driver program, you started at driver entry. And that's where you start with this reverse engineering process, or at least where I do. And you can see that it sets up the device in AFD device off of the devices tree in Windows. You can see that it pulls a bunch of information from the registry, which I thought was kind of curious. It's not uncommon to see devices storing things in the registry. It's a perfectly logical place for it. But the sorts of things it was storing were suspect. So things like the maximum buffer size for a address name, and the medium buffer size length, and how many workers should I have running. This thing was configuring itself from the registry for how it should operate. And I don't know if this was a distinction to make the same code run in a server environment and a user mode environment, but it has about 50 configuration parameters that are pulled out of there. And just a simple string, if you run strings on the binary, you will see all of those parameters grouped together in the same section of memory. The one that I had actually seen before and kind of forgotten about was this disable raw security flag. So if you are in Windows and you wanted to, say, write a program that would send an ICMP packet, a ping packet, to do that, you have to have a privileged process. And that is because ICMP packets will need to open a raw socket. You can't, after XP Service Pack 2, you couldn't open a raw socket in Windows anymore unless you were privileged, unless you have this registry key bit set. And you see a lot of Nmap guide for Windows will tell you to set this bit and another one in TCP/IP parameters, which loads the same sort of sets of things from the registry. You just don't see it. You don't see what's there because there's no keys set by default there. Everything is blank, and all the reads fail, and then it uses default values for everything. So these are some of the deep Windows internal configuration parameters that you can find just by poking around for a couple hours with the driver. This is also interesting that a few of them were labeled as volatile configuration parameters, and this was a separate data structure in Windows that the driver registered a change event notification. So you can set up an API that will give you a callback anytime a registry key changes. And this is useful for lots of different things. Someone updating configuration, AFDsys, you register for a change event and your function gets called, and you can reinitialize your parameters. And if you're not careful about this, especially with things like buffer sizes, you could change these parameters as the device was running, and suddenly your maximum buffer size grew between when a function call was started and a function call was ended due to context swapping. So this was interesting to me. Unfortunately, well, fortunately for the defender, unfortunately for the attacker, all of these are appropriately secured. So you have to be an administrator to touch these registry keys. And that sort of said to me, well, I'll move on to more important things because we're talking about sandbox escapes. And we're certainly not administrator escaping a sandbox. We can barely write a file, let alone a registry key. So leave this as an interesting tidbit and move on to other attack surfaces. So if you wanted to go back and look at this and try interacting and fuzzing the driver, this would maybe be one way to find an elevation from admin to kernel in a Windows environment. So we know that it pulls input from the registry. What else can it take in? What else does it do? And really, there's these 6 lines of code that sort of define where it can take input from. So this is ripped out of IDAPRO, the hex-arrays disassembler. On the driver object, there's this table of functions, and it's setting all of them with memset32 to AFD.dispatch. So all of them are dispatched in the beginning, and then for device controls, it goes to AFD.dispatch device control. There's this internal device control, which is WSK sockets. For win.kernel, goes to this internal one only, so you can't actually call this from user mode. That function offset, the IRP MJ internal device control, is only accessible from kernel mode calls. So that's not an available attack surface from the sandbox. And the event dispatching or event tracing for Windows is set in there as well. This is kind of cool. There's a fast I/O path, which is normally something you see in file system drivers. So this is like, you've read this file twice, I already have this cached, I don't need to make any calls out to hardware, I can just give you the information right away and return very quickly. So they have this fast I/O path in here. And for the most part, it just maps to the existing I/O controls, the ones that return immediately. There's an unload, which is kind of mandatory for drivers. So beside the ioctls, which are all set up here, ioctl is I/O control code. If you haven't seen it, it's usually like a number. So an I/O control code for AFD.sys would be 1206F. And that says to the I/O manager that this is an I/O control for actually the beep system driver, or the 1 would be where it was going, but that's not used because you're sending it to a device that was opened by something else. And then it also says how data is transferred. So there's 3 methods for transferring data in the Windows kernel. There's 2 buffered methods where it can be, the buffers are managed by the I/O manager, and then there's a third one called method neither, which is really what you want to look for if you're looking for exploitable device driver conditions, because that's like Linux copy from user. It's completely self-managed. You get user mode pointers into kernel mode, and that is up to the driver to ensure that everything is safe and secure. And that's been a large portion of bugs in Win32k-sys have come out of that, where you have essentially a time of check to time of use bug, where you have a bit of user mode code, or a bit of user mode data that is checked in kernel mode, and then it runs a little bit and gets pulled again for usage. And the problem is that between the time it's checked for a valid value and the time that it is used, another user mode thread can come along and change that value. And there's some tricks about how you can encourage a context swap to win that race more often, but seeing method neither on these ioctals was a key to look for those kind of bugs. So time of check, time of use bugs. Additionally, AFD seems like it really wants to maintain a list of all of the IP addresses on your system. So it wants to know if you have IP, IPv6 addresses, and it has registered events with, then there's like a network pluggable management system that it'll get a callback when that changes. There's a event with TDI that it will get a callback when it changes. And there's also plug-and-play events that it will get a callback when a new network card is inserted. So you plug in like an infrared transmitter or a wireless USB device. It's going to get a call from that interrupt up to AFD.sys. And this was kind of interesting too. This is a relatively new thing in the Windows kernel. It supports RPC. You know, this sort of you see on port 139 RPC calls, but in the kernel locally. So that's something I want to investigate more, and it's on my future work to-do list. But there's another device driver that's supporting this called MSRPC.sys, and you can just see which drivers import it and follow it through there. This is on the right-hand side is really what the ioctal table looks like. This is the complete list of functions. This is really, really easy to find. There's one cross-reference to this off of this dispatch, and it's there. And then immediately following it are the ioctal numbers that match up to this. So just down below this, there's the first ioctal number that matches up to this first function AFD bind. So if you wanted to call AFD bind from user mode, you would then create a handle open to the device AFD some endpoint name, and then you do device IO control with the first ioctal number there, and you could step through it in a kernel debugger at that point. There's one interesting little pattern, maybe some of you see it, that these are all the same, and there's a bunch of them down here that are the same, and the same to here. So they have like the same function called for like 30 different IO control codes, and that didn't quite make sense to me, so I dug into a little bit more. And what this is, there's another level of indirection here. So this is the first table, so it starts at AFD bind. It comes down here, and this AFD dispatch immediate is the one that's been repeating. And if you go read the code for AFD dispatch immediate, you find that there's actually another table that is implemented here. And so AFD dispatch immediate here maps to AFD partial disconnect, and this one maps to query receive information. So that second layer of indirection, I wondered why they did that, and the dispatch immediate kind of tells you it's for functions that always will return right away. So when you receive requests as a driver, you can say, yep, pending, I'll get back to you when that returns with a blocking request. Or you can say, yep, here's your data right away. And for the functions that say, yep, here's your data right away, all of them go through dispatch immediate indirection. The more interesting thing here is there's a third level on top of this, and that is that inside of the dispatch immediate, there was one function that was repeated 6 times. And okay, it's not called dispatch. There's no other function table. Inside of that function, it actually looked at which ioctal was for what, and it had a common code base at the top, and then it did SAN request is what it was for. All of the SAN requests were implemented for getting information in this one function. Right, so bug hunting. This is the part that I tend to enjoy the most. I primarily targeted Windows 7, x86. I'm faster with 32-bit code, and the decompilers seem to work better on 32-bit code, so this is what I went for. I started with the basic tricks. So bottom-up analysis. You load up the driver, you say, where is memcopy called? And you find memcopy, you press X, you get a list of 80 cross-references. And you go to the first one, and you say that length is 32. And it's going to copy 32 bytes from some buffer to another buffer. How big is the buffer that it's copying into? And if it is 32 bytes or greater, then it's safe, and you move on to the next one. So you do that 80 times, and then you move on to the next API call, which was memmove, which is the next one I looked at. Thankfully, there are only 12 cross-references there, and this is a process you can automate to some extent. I like to do this manually because it gives you a sense of the driver and what it's doing. So if you find a mem copy statement that is imported rather than inlined, you will have familiarity with the code that you've been through once before if you're doing a more high-level reverse engineering for functionality. The stack cookies. So stack cookies are a protection /GS that you can enable with the Microsoft compiler. They are designed to have a canary value that if it gets corrupted, you terminate the program, terminate or blue screen in this case, and then you don't continue execution into a corrupted stack frame, which is a very, very easy way to gain control of a piece of software. But it's expensive to do these checks, right? So there's a memory fetch, there's an XOR, there's a compare, and there's an extra jump that's there. So the compiler realizes that this is a performance hint, and to put them on every function would be too big of a slowdown. So they put them on only some functions. And these happen to be the functions that are doing the most work with stacks. So it'll say you have a character array on your stack. I'm going to put that at the end, and I'm going to put a canary right after it. And security check cookie cross-references will tell you all of those functions that are doing a lot of work with the stack. So I don't have to go looking for these things manually. The compiler told me where I should look. And you go back through those functions, and there's only a handful of them that actually use it in this driver. Most of the allocations are done on the heap or the kernel pool. The other big thing that I like to look for when I'm doing like first initial analysis is which functions have large stack frames. So who put a 2 kilobyte buffer on the stack, and in the kernel that's a kind of an unwise thing to do. So I went through and looked at every stack buffer greater than like 5K, and then you move that number down, 5K, 2K, 1K, greater than 512 bytes and 128 bytes. You move that number down until you find that it's no longer productive to look at. The other thing I looked for with some degree of automation was unchecked return values. So in user mode code, you would call malloc, and you'd get a pointer back. And if you don't check that that pointer was not null, you can have a null pointer reference. So you could write data to null given back from malloc if you don't say, did you give me back null or did you give me back a pointer? So the same thing happens in the Windows kernel. There's this routine ex allocate pool, and there's with tag, with quota tag, with priority. There's like 7 or 8 of them. You go through them all. They're very easy to find in the imports. They're all grouped alphabetically. And you check them to see, did you check the return? And this is something you can automate in IDA with a Python script that will say, yes, there was a test after this call and a jump, or there wasn't. And a couple of them didn't quite match up, but there was only 3 that didn't match up to that signature of call allocation routine, check for a test instruction, if not, and then jump somewhere else. There was one exception that kind of caught me before. This was with this ex allocate pool tag with tag priority, which behaves differently from all the other allocation routines. It doesn't return a null pointer when it fails. It throws a C++ exception, which there has to be a registered exception handler for in the program, or else it's going to have the same issues. But I thought I had a bug on like day 2 when I saw this unchecked allocation return. And that's sort of the nature of vulnerability analysis, is you have these high highs of, oh, I got a bug, and you have these low lows when you realize you were completely wrong. And but you learn something in the process, hopefully. So you repeat until you either burn out and are defeated by the driver, or you get what you're looking for in the first place. And those are sort of like the cheap tricks. Most of the people at Microsoft are writing code that's better than this now. Like, people know about dirty dozen APIs. They know not to use them. Microsoft has specific hooks in their compilers to say, oh, don't use that API anymore. And it's built into their security development lifecycle. That's what that kind of bug eliminates, is those low-hanging fruit bugs. So the next thing I did was a manual review of all of the reachable ioctls from a sandbox. And those are the big table. I went through everyone and all their functions that they called down to level 3, so depth of 3 function calls. And I checked for issues like if you're receiving a pointer from user mode and a method neither call, is the data on a 4-byte alignment, right? Because if it's not, that can cause issues if you hit, like right up against the edge of a user mode, kernel mode boundary. They did a very good job with this. Every single buffer I saw was checked for alignment before it was ever used. Were there proper size restrictions used? Most of these calls limit the amount of data you can pass in to 256 bytes. If you pass in more than that, it kicks you out pretty much the first thing along the way, which is a very effective way of defending a driver. I checked for these time of check, time of use bugs with method neither ioctls. And then the one that hasn't really been automated out of Microsoft code yet is the integer issues. So if you're looking at Microsoft code, really pay attention to where they're using 16-bit values or where they're sign extending a value so that you can get a large number that is represented as a negative number with a like move SX instruction. Nothing I found or nothing I looked at looked like it had potential to be hit in a bad way. And at this point, I was growing frustrated and feeling down about my level of analysis ability. So I decided to fuzz the thing, which is not my preference. I usually like to do static and dynamic analysis on the driver. I feel like it gives me a better understanding of how it works. And the one benefit I will say is that if you do static analysis first, even if it's just a day or two of static analysis, you're going to write a better fuzzer, right? Because you're going to know that if I send in more than 256 bytes to this thing, it kicks me out. So my fuzzer won't do that, and I'll skip a whole lot of bad calls that I otherwise don't need to test. I spent 2 weeks fuzzing it only on a single core. I hit all of the ioctals, the fast I/O, the dispatch immediate ones, the regular dispatch ones. And I knew that because I had these method neither calls, I wanted to really probe for these time of check, time of use bugs with the fuzzer. So what I did was I had the data that was passed into this driver was mutated by another thread running. So the fuzzer was actually running completely outside of the ioctal calling routine. So I had a for loop calling the octals with a buffer that was changing according to randomness. So you flip a couple of bits off of a valid call, make the call, see what you got back. Again, turned up nothing, but I don't feel like 2 weeks on a single core is a whole lot to do that justice. But we didn't scale it because we didn't have any sort of success with this. So getting like code coverage metrics out of this would be a really useful thing to do, because you'd know how effective one particular input was versus another, and then that's something you could scale. But this would actually still be classified as a dumb fuzzer, even though it has kind of a clever technique. From the sandbox, it's possible to interact with this device. Therefore, it is possible to create sockets, even if your sandbox doesn't want you to be able to create sockets. So I have this knowledge built up from this fuzzer about how to do these calls, what they are expecting, and it is certainly possible to build a native API for AFD.sys so that you don't have to go through WinSock to make a socket. You could link against a piece of code that would make these ioctals directly to AFD.sys in an appropriate way that you could do basic communications. And this is actually something that I think is an interesting attack tool, which makes me hesitate on releasing it a little bit, because this could be compiled directly into shellcode that would be used in an attack. So the merits of that are up for debate. However, I do think that the more ioctals you build out in a library like this, the better you would be able to fuzz in the end. So more fuzzing, at-scale fuzzing, more expected data structures defined. I only defined about half of the ioctals, so the other half would need to be defined as well. And then the functions that were not reachable from the sandbox are probably still worth a look. In particular, the sand functions. I think those would be valuable to go through manually. And the WSK, I'm just kind of curious about how it works. And if I ever find the time to get back to this, I will give those a manual review as well. So a big thank you to Google, who put up with me reversing this driver and not getting anything to show for it for about a month. Project Zero, my team, was really helpful and supportive of guiding me in the right way. What would they do to fuzz it? How could we fuzz this at scale? Is it worth doing these things at lots of different decision points along this process? And then James Forshaw was, credit where credit is due, he's a fantastic Windows reverse engineer and vulnerability analysis, found the AFD accessibility from the sandboxes in the first place. And he's released a suite of tools that if you have a program that uses a sandbox, you can actually go pick those tools up and it will tell you everything that's accessible. So it walks through the object manager and it tries to interact with all of the objects, pulling, yes, I can interact with AFD, yes, I can interact with the COM port or your USB hub. And those are maybe things that you don't want an attacker to have access to from inside of a sandbox. So James is great. I suggest looking at some of his talks. He had a good one at ShmooCon that touched on a lot of these similar issues. With that, this was a 25-minute talk that landed in an hour time slot. So that's the end of the presentation, but I'm happy to entertain questions for the next half an hour if there are desires to do so. Yes? Good question. So the question was, did I write a custom fuzzer, or did I use something like Peach or Sully to fuzz it with something that you could download and look at yourself? No, I wrote this by hand. Took the list of ioctals and their names and built the data structures that they were expecting and did the calling myself. It's actually not too bad to do that because it's a for loop over the ioctal numbers and then a device IO control call with each iteration through that. Yeah, so that's another. How do you get metrics out of your fuzzer, or how do you find success? Because you don't want to just have one day, you wake up and you've been running your fuzz run overnight and you found that you had a blue screen. How do you reproduce that? What happened? So the easiest way possible is the answer, and that was the target I was fuzzing had a kernel debugging connection back to another machine that would catch that exception when it faulted. At which point I'd have the fault in the IP, and I could reverse engineer where the problem was with that. I didn't record input. I didn't record random seeds, mostly out of concerns for speed. Yep, any other questions? Thank you, those are good questions. Great, well, thank you very much, guys. Appreciate you turning up at 10 a.m. on a Sunday morning after a long night of open bar. So hope to see you at next Circle CityCon too.